Welcome to the topic of particles and radiation. In this section, we explore the smallest building blocks of matter, how particles interact, and how radiation can be produced and detected. We will learn about fundamental particles, antimatter, particle interactions, and the evidence that supports our current models of physics. Specification overview and learning objectives, constituents of the atom and atomic models, specific charge of fundamental particles, isotopes and nuclear composition, the strong nuclear force, stable and unstable nuclei, alpha decay, beta-minus decay and the neutrino, particles and antiparticles, photons and electromagnetic radiation, annihilation and pair production, classification of particles, quarks and antiquarks, the four fundamental interactions, the photoelectric effect, energy levels, and line spectra, wave-particle duality and exam summary. Students are expected to understand both qualitative descriptions and quantitative relationships, supported by equations and graphical interpretation. The topic is divided into two main strands: particles, including atomic structure, nuclear stability, antiparticles, and quarks, and electromagnetic radiation with quantum phenomena, including photons, photoelectric effect, and wave-particle duality. Throughout this topic, students must apply conservation laws, including conservation of charge, nuclear number, and energy, particularly in nuclear and particle interactions. Practical skills are also embedded, such as interpreting decay equations, analyzing experimental evidence for photons, and understanding how detectors such as Geiger counters and PET scanners operate. Atoms are the basic building blocks of matter and consist of three fundamental constituents: protons, neutrons, and electrons. In the simple atomic model, protons and neutrons are located in a very small, dense nucleus at the center of the atom, while electrons orbit the nucleus at relatively large distances. Protons carry a positive charge of plus 1.6 times 10 to the power of 1c, neutrons have no charge, and electrons carry an equal and opposite charge of minus 1.6 times 10 to the power of 1c. In terms of mass, protons and neutrons each have a mass of approximately 1.67 times 10 squared kilogram, while electrons are much lighter at 9.11 times 10 cubed to the power of 1 kilogram, making their mass negligible in most nuclear calculations. The proton number, Z, defines the element and represents the number of protons in the nucleus, while the nuclear number, A, represents the total number of protons and neutrons. Specific charge is defined as the charge-to-mass ratio of a particle and is a key quantity in particle physics. It is calculated by dividing the charge of a particle by its mass, giving units of c kilogram to the power of 1. For example, the proton has a charge of plus 1.6 times 10 to the power of 1c and a mass of 1.67 times 10 squared kilogram, resulting in a specific charge of approximately 9.58 times 10 c kilogram to the power of 1. In contrast, the electron has a much smaller mass but the same magnitude of charge, giving it a significantly larger specific charge of about minus 1.76 times 10 to the power of 1 to the power of 1 c kilogram to the power of 1. This large difference explains why electrons are much more easily deflected by electric and magnetic fields compared to protons. Isotopes are atoms of the same element that have the same proton number but different numbers of neutrons. Because chemical properties depend on electron configuration, isotopes of an element behave identically in chemical reactions, but their nuclear properties can differ significantly. Some isotopes are stable, while others are unstable and radioactive. For example, carbon-12 and carbon-13 are stable isotopes, whereas carbon-14 is radioactive and undergoes beta decay. Isotopic data is often presented in tables showing relative abundance, which is used to calculate relative atomic mass. In nuclear physics, isotopes are important because the ratio of neutrons to protons influences nuclear stability. The strong nuclear force is the fundamental interaction responsible for holding protons and neutrons together within the nucleus. Despite the strong electrostatic repulsion between positively charged protons, nuclei remain stable because the strong nuclear force is much stronger than the electromagnetic force at very short distances. This force acts between all nucleons and has a very limited range of approximately 3 femtometers, 3 times 10 to the power of 1 m. A nucleus is considered stable when the balance between the strong nuclear force and electrostatic repulsion results in no spontaneous decay. Unstable nuclei, however, have an imbalance in the number of protons and neutrons, or are too large for the strong nuclear force to hold them together effectively. As a result, they undergo radioactive decay to reach a more stable configuration. The stability of a nucleus depends strongly on the neutron-to-proton ratio, particularly for heavier elements. Light nuclei tend to be stable when the number of protons and neutrons is roughly equal, while heavier nuclei require an excess of neutrons. Unstable nuclei emit radiation in the form of alpha particles, beta particles, or gamma photons. These decay processes are random and spontaneous, unaffected by external conditions such as temperature or pressure. Alpha decay occurs in large, heavy nuclei that have too many protons and neutrons to remain stable. During alpha decay, the nucleus emits an alpha particle, which consists of 2 protons and 2 neutrons and is identical to a helium-4 nucleus. As a result, the proton number of the parent nucleus decreases by 2 and the nuclear number decreases by 4. Alpha particles are highly ionizing due to their large mass and charge, but they have very low penetration and can be stopped by a sheet of paper or a few centimeters of air. Beta- decay occurs in nuclei that are neutron-rich, meaning they contain too many neutrons relative to protons. In this process, a neutron in the nucleus transforms into a proton, emitting an electron, beta particle, and an antineutrino. The proton number increases by 1, while the nuclear number remains unchanged. The inclusion of the antineutrino is essential to conserve energy and momentum, as observed experimentally. Beta particles are moderately ionizing and have greater penetration than alpha particles, typically being stopped by a few millimeters of aluminium. The neutrino has very little mass and no charge, making it extremely difficult to detect. For every type of particle, there exists a corresponding antiparticle with the same mass but opposite charge and other quantum properties. For example, the antiparticle of the electron is the positron, which has the same mass as the electron but a positive charge. Similarly, protons have antiprotons, neutrons have antineutrons, and neutrinos have antineutrinos. Antiparticles are produced in high-energy environments such as particle accelerators and certain types of radioactive decay. When a particle meets its corresponding antiparticle, annihilation occurs, resulting in the conversion of their mass into energy, usually in the form of gamma photons. Electromagnetic radiation can be described using the photon model, where energy is transferred in discrete packets called photons. The energy of a photon is given by the equation E equals hf, where h is the Planck constant and f is the frequency of the radiation. Since frequency and wavelength are related by c equals f, photon energy can also be written as E equals hc lambda. This relationship shows that higher frequency radiation, such as gamma rays, carries more energy per photon than lower frequency radiation, such as radio waves. Photons have no mass, no charge, and always travel at the speed of light in a vacuum. The photon model is essential for explaining phenomena that cannot be accounted for by classical wave theory, including the photoelectric effect. Annihilation occurs when a particle meets its corresponding antiparticle, resulting in their complete conversion into energy. For example, when an electron and a positron annihilate, they produce 2 gamma photons, each with an energy of 511 keV, emitted in opposite directions to conserve momentum. Pair production is the reverse process, where a high-energy gamma photon interacts with a nucleus and produces a particle-antiparticle pair, typically an electron and a positron. For pair production to occur, the photon must have energy of at least 1.02 MeV. The presence of a nearby nucleus is required to conserve momentum. Although E equals mc squared underpins these processes conceptually. Fundamental particles are classified into 2 main groups, leptons and hadrons. Leptons include electrons, muons, neutrinos, and their antiparticles, and they do not experience the strong nuclear force. Hadrons, on the other hand, do experience the strong force and are further divided into baryons and mesons. Baryons, such as protons and neutrons, are made of 3 quarks, while mesons are made of a quark-antiquark pair. This classification helps physicists understand particle interactions and decay processes. Quarks are fundamental particles that combine to form hadrons. There are 6 types of quark, known as flavors: up, down, strange, charm, top and bottom. Protons consist of 2 up quarks and 1 down quark, while neutrons consist of 1 up quark and 2 down quarks. Each quark has a fractional electric charge, either plus 2/3 or minus 1/3 of the elementary charge. Antiquarks have the same mass as their corresponding quarks but opposite charge. Quarks are never found in isolation due to a phenomenon called confinement. All physical interactions can be explained using 4 fundamental forces: gravitational, electromagnetic, strong nuclear, and weak nuclear. Gravity acts between masses and has infinite range but is extremely weak at the particle scale. The electromagnetic force acts between charged particles and is responsible for electric and magnetic effects. The strong nuclear force binds quarks together and holds nuclei intact, while the weak nuclear force is responsible for beta decay. The photoelectric effect provides clear evidence for the particle nature of electromagnetic radiation. It occurs when photons incident on a metal surface transfer energy to electrons, causing them to be emitted. A key observation is the existence of a threshold frequency. Below this frequency, no electrons are emitted regardless of intensity. Above the threshold, increasing intensity increases the number of emitted electrons, while increasing frequency increases their maximum kinetic energy. These results cannot be explained by classical wave theory. The photoelectric equation, HF equals phi plus Ek, max, relates photon energy to the work function of the metal and the maximum kinetic energy of emitted electrons. Electrons in atoms occupy discrete energy levels, and transitions between these levels result in the emission or absorption of photons with specific energies. When an electron falls to a lower energy level, a photon is emitted, producing an emission line spectrum. Conversely, absorption spectra occur when photons are absorbed, causing electrons to move to higher energy levels. The energy of each photon corresponds to the difference between energy levels, given by E equals HF. Line spectra provide strong evidence for quantized energy levels and are used in applications such as chemical analysis and astrophysics. In this topic, we have explored the particles that make up matter, how they interact, and how radiation is produced and used. Understanding particles and radiation helps explain the structure of the universe and many modern technologies. Thank you for watching.